Okay, so in the previous video, we were computing the convolution product, so using this given formula of our two functions, so a function f, which had no specific requirement for the moment, and our rectangle function, the get function, this one, the pi function, which is just a constant function with an area of 1 on an interval well, b minus ab. Okay, so we did the calculation, we obtained this, and we got that that was the formula of the convolution of f with pi, with that pi, and that makes a function of x. Okay. I've also already given the interpretation of this convolution as the moving average of the function f on an interval of size b minus a. Okay, all right. So one of the first property that we can see about this specific convolution is that it's kind of smoothing the function. What do we mean by this? Let's see, if the function you started with, your f is c0. Let's see what we can infer about the regularity, the smoothness of f convolved with pi. Okay, so let's look at this integral that we have here. All right, so obviously if f is continuous, this is going to be well defined. Furthermore, applying differentiability in x of this, so I've got 1 over b minus a integral between x minus b, x minus a f of t dt. That's going to be, well, d over dx of 1 over b minus a. So if I know some primitive function of small f, that let's call that big F, it's going to be big F at the point x minus a minus big F at the point x minus b. And finally, if I do the derivative of that with respect to x, I've got, well, the derivative of the antiderivative. So I'm getting back my function f x minus a minus f x minus b divided by b minus a. Okay, so what can we see? Well, sorry, that's a small f. So obviously, if the small f was continuous, the derivative of the conversion f with pi is also going to be continuous. So that means that f convolved with pi is actually a C1 function. Okay, so we have what we could call a smoothing effect of the convolution. Okay, that's also something maybe you could see on the animations of Wikipedia that we saw earlier. Okay, and well, that's it. Another thing that we can see is that if we have that b tends to a, if b tends to a, what do we have? Well, to a by positive values, we have that the convolution of f with the pi function, so on the interval ab of x, tends to, well, you get, using the same notations of as before, the limit as b tends to a of f of x minus a, big F of x minus b, divided by b minus a, which is actually x minus a minus x minus b. Okay, so do you see where I'm going there? That's good. That's the increase of the function divided by the size of the interval, because this is really b minus a. So that tends to the derivative of that big F function at point A. So that tends to f of x minus a. And we may wonder what this function pi looks like when b tends to a plus. Well, let's say it begins like this. If you've got a and b, and then you want to keep the same area but increase your functions, but so you want to keep the same area, but b tends to a, so you're going to have something bigger and even then bigger and so on. So you're getting to get some function that has a very small support, where has a bigger and bigger values. And we're going to see that this is also some interesting functions, but we'll talk about this maybe later in the distributions chapter. Okay, let's go back to this document and explore some of the properties of the convolution. All right, so this one. First, this this property, sorry, it's ugly. This property that tells you that f convolved with g is equal to g convolved with f. That's interesting. Yeah, that means if you're using the same kind of definition of description that I gave earlier by saying it's how the shape of one is modified by the other, think of this as being a symmetric relation. Okay, the same way as if I convolved my function, any function with a rectangular function signal, I would get some average. Some moving average of my function. Well, you can see it also as saying how your function is going to modify your constant value, okay, as it shifts through the area where this constant value is non-zero. Okay. However, how can we show this first property? Obviously, if you write f convolved with g of x, that's going to be the integral of f x minus y, g of y dy, and g convolved with f, that's going to be the integral of g x minus y f of y dy. So let's write the bounds, negative infinity plus infinity. So maybe we can just do some simple substitution. Put capital Y is equal to x minus small y. Okay, so then we have that d big Y is going to be minus dy. So now let's plug this substitution. That's going to be, so when small y is negative infinity, big Y is going to be x minus negative infinity. So x plus infinity, as x is supposed to be any value, any bounded value. So that's making it to go from plus infinity. And upper bound is going to be now small x minus plus infinity. So x minus infinity, so which is minus infinity. Right, so that's the bounce. Obviously, it's going to be bounced back by the negative sign that I get from the substitution. And then my function g becomes g of capital Y. F of y is going to be, so small y is going to be given by x minus big Y, so x minus big Y. And here we go, we just have to bounce back the bounds using the minus sign in front of the integral. And here we have the first formula that we, and maybe if you really want to use again the same letter as it's just dummy variable, you can keep the capital Y or just get back to the small y. It's just a dummy variable of integration. Okay, next in the properties we have, well, linearity. If you do the convolution of some function g with a combination, a linear combination, alpha f1 plus f2, that's going to be alpha convolution of with the first one plus the convolution with the second one. Okay, next comes a property that tells you that the integral of a convolution is the convolution of the primitives. I think that's, we should rather read it this way. Okay, well, you can prove it with a bit of elbow grease and using substitution again, I guess. All right. What else can we say about convolution? Okay, we've got the next theorem, which is quite interesting. Okay, what does it tell you? It tells you that if f is in L1 and g is in LP, then the convolution of f with g belongs to LP, and the convolution of f with g, the p norm of that is going to be bounded by the norm 1 of f times the norm p of f of g. Oh, sorry, there is a typo here. That should be the norm p of g. That should even be more than that. It should be written like this. Okay, so and all right. So let's say that it's just not too complicated to show. It's just an extension of Cauchy-Schwarz actually. But what is very important is this property. If P is plus infinity, what does that mean? If G is just essentially bounded, okay? So that's not asking for too much. I'm just looking for a bounded function, right? Then the convolution of f and g is continuous. So if f is in L1 and g is bounded, then we get a continuous function, even if the f you plugged in was absolutely not continuous. You remember that L1 is just f belongs to L1, just means that the integral of the absolute value of f is bounded. Okay, so that's what does it say? It's really regular smoothing. It brings regularity to some input function, and that's even a way to smooth some signals, right? That could be very not continuous, and you can use convolution to sort of blur your signal locally so that it gets continuous. So this part we can prove. I mean, in the case where we've got f in L1 and f in L1 and g in L infinite. So first, let's look at f convolved with g, the infinite norm of that. That's going to be okay, so this is equal to the let's look for the supremum of absolute value of the integral f x minus y g of y dy. Or, as you know, you can also write it as the supremum of that's f convolved with g, but it's also equal to g convolved with f, so I can exchange the rules of x and x minus y. So that makes f of y g of x minus y dy. Why do I do this? Because I know that if g belongs to L infinite, I've got that g of anything is going to be in absolute value smaller or equal to its infinite norm, right? That's just because the infinite norm is the supremum. So that stuff, okay, well, I mean, the integral of, well, that's just integral of absolute value of f convolved with g. That's going to be smaller or equal to the infinite norm of g times the integral on R of, let's keep the absolute value, of f of y dy. Okay, and of course the absolute value of the integral is smaller than the integral of the absolute value, so that's going to be smaller or equal to integral on R of absolute value of f of y dy, and you all have, oh, sorry about this, you all let me erase that. That was some previous stuffs. You all have noticed that this actually is equal to the L1 norm of f. Okay, so under our hypothesis that we said, we have that it's going to be smaller than g infinite f1, the for all values of x, f convolved with g is going to be smaller than this, and so if that works for all values, that also works for the supremum, so the infinite norm of f convolved with g is smaller than that. Then we have that second part, which is very, very important and that you have to really remember correctly, is that if f is only L1 and g is only L infinite, then their convolution product is continuous. So this takes a bit of work to to prove. We won't have time to do it. Actually, well, I think it's not necessary that we do it. The correct proof is using approximations with simple functions. But let me show you some idea. If your two functions are already continuous, of course, you could just apply Lebesgue's theorem, right? Well, dominated convergence. I mean, the extension of that theorem for parameter-dependent integrals. Okay, so that seems pretty clear. That if that stuff x minus y g of y is continuous, that would be one requirement. Then you have that this is going to be continuous also, just by applying the usual theorems. What do we need if this is continuous, which is not the hypothesis we wanted, but if it is, which is a stronger hypothesis, and still you get that f is L1 and g is L infinite, so you just need to find the dominating function, and again we just write that. Let's exchange the rules of the x minus y and y, so that's f of y, g of y, and we do exactly the same stuff as before to find a dominating function. What is our dominating function is going to be, x minus y, g of x minus y, our dominating function is just going to be the infinite norm of g times f, absolute value of f of y. Okay, and of course, as f belongs to L1, that's that's a dominating function that is integrable. Okay, dominating function. All right, so but that works only if f and g are continuous, and so that's not a big deal. What's a big deal is that even if you plug in non-continuous functions, the output of the convolution product makes a continuous function. So if you want to prove that rigorously, you have to use some approximation of g with simple of f with simple functions. Okay, and then in the end, it's going to work. But that's it for our continuous convolution product.